Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the next in a series on exponential and logarithmic functions. You should have already watched my videos on exponential functions, kind of a review of them, the types of exponential growth and decay we're going to see, solving exponential equations, and compound interest formulas, and dealing with the natural base, all that fun stuff. So now we're going to deal with the more mathematical aspect, kind of the true basic mathematical aspects of exponential functions, the graphing part of it. And because most of us struggle with graphing, it's important we spend some time reviewing this. And again, this should be review. So graphing exponential functions. As you should recall, but if you don't, here it is. There's some properties or characteristics of graphs of exponential functions. The graph of the exponential function p of t, which is p naught b to the t, has the following characteristics. I should note, and I don't know if I mentioned this in the previous videos, I probably did, but if I did not, I don't use the same format that most authors use when they talk about exponential function. Most authors use the format f of x equals ab to the x power. It's the same thing. It's just that honestly, exponential functions are usually functions of time, and they usually return, or their function values are, populations. So a population of a species, a population of bacteria, whatever it may be. So that's why I use this p of t equals p naught b to the t notation. Anyhow, let's see some properties of the graph of an exponential function. The graph is going to be a one-to-one function. Or I should say p itself is a one-to-one function. So the graph should pass the horizontal and vertical line tests. If you don't recall that, you could go and watch my series on inverse functions where I talk about one-to-one functions. Let's see what else. P has a horizontal asymptote at y equals 0. Again, if you don't know what a horizontal asymptote is, you should watch my video series on asymptotes. And that would be in the rational functions series for the college algebra student. The domain of our exponential function is all real numbers. Again, if you don't recall what domain is, watch my video series for college algebra students on domain and range of functions. The range of our exponential function is 0 to infinity typically. And I say typically because usually you're dealing with a positive initial population. It's not very realistic for somebody to tell you, I have negative 13 cats and it's growing at this rate. That just doesn't make sense. So you'll have negative initial populations only in math courses. And that's why I tend to avoid them. I'm a mathematician at heart, but I'm also an applied mathematician by trade. And so I like the real world mathematics, and I like to make sure that what you learn is applicable to the real world. So p naught being negative is not a realistic situation. However, if you're handed p naught being negative, then the range is negative infinity to 0. Remember, exponential functions will never become 0 unless you have some type of vertical shift going on. They will not become 0. Let's see, the fifth thing, p has a vertical intercept at 0, p naught. That can be mechanically evaluated. The vertical intercept of any function can be found just by evaluating the function at time 0. And you would see you have p naught be the 0, but b to the 0th is going to be 1. Mainly because b is non-zero, and so therefore that will be p naught. So 0, p naught is on the graph of our exponential function. What else we have going on? The graph contains many other points, obviously an infinite number of points, but one of them is 1 comma P naught B. I would not memorize that. It's just there for your information. And finally, assuming that the initial population is positive, which is almost always the case, P is increasing if the base is greater than 1, and it is decreasing if the base is between 0 and 1. And that just repeats something that we had mentioned previously, that if you have an exponential function with a base greater than 1, you have exponential growth. If you have an exponential function with the base between 0 and 1, you have exponential decay. In the very rare case where your initial population is negative, these properties are reversed. I will probably never showcase that except for a theoretical, like mathy example that you would see in a math textbook. So here we are. We've arrived at our destination. We're told to graph this exponential function. And you look at that and you say, but they're decimals, so I need a calculator. No, you sure don't. All you need is a couple points, and you need to know whether this is decaying or if it's increasing. In other words, do you have exponential decay or do you have exponential growth? The fact that this base is less than 1 and positive will imply we have an exponential decay, and therefore our curve, our exponential function, is decreasing. Otherwise, everything else is kind of par for the course. Usually when I see an exponential function and I identify whether it's increasing or decreasing, I then very quickly sketch out the x-axis here. Actually, is it x? Nope, it's a t-axis. I'm following my lettering, and a y-axis, and it is a y-axis actually. When I was a student, I really got confused about this. I thought it was the p-axis is what I would say, and it turns out that the y-axis is almost always just called the y-axis. The horizontal axis, on the other hand, is the independent variable that they've handed us. However, the output is y equals P of t. So just to let you know, I mean, I don't care if somebody calls it the p-axis, to be very honest with you, but it's just one of those things in practice, you'll rarely see somebody call it the p-axis. They'll still call it the y-axis. Kind of annoying, honestly. And we know this is a decaying function. So in blue, I'll just draw in a decaying exponential function. Notice I didn't plot a single point. I just drew an exponentially decaying function. After I'm done drawing that, now I'll plot a couple points. The y-intercept is something I will always plot. And then something at x equals, or in this case, t equals 1. That's it. So 0 comma and 1 comma. And to figure out what those values are, it's very fast. P of 0 is going to be 1.1 times 0.8 to the 0th power, which is 1.1. And if I plug in 1, I get 1.1 times 0.8. Now that obviously would require a calculator, or you could actually multiply that by hand if you want to. In either case, it's going to be a 0.88. Excuse me. Notice 0.88 as a y value is less than 1.1. So it does make sense. And also notice here that the way I drew this function, it is decaying to a height of 0. Because remember, from our rules, our kind of properties on this page here, that P has the horizontal asymptote, let me highlight where I'm looking at, of y equals 0. So I know that as time goes on, the y values will want to tend to a height of 0. Also, the range is going to go from 0 to infinity, so I know it's never going to touch 0 as an output. And that's exactly what this graph looks like. I'll draw in the horizontal asymptote, although there really is kind of no point to draw in a horizontal asymptote when it's approaching just the t-axis here, but I'll just say this is a height of 0, just so everybody knows that I know there is a horizontal asymptote. Ladies and gentlemen, that is as crazy as it gets for a basic exponential function. Whether it's increasing or decreasing, it's that fast. Nothing crazy about it. But then you say, well, I know my teacher's cruel and they're going to ask me a question that involves transformations. And I'm one of those teachers too, so I should probably do a problem just like that. So here is a problem with transformations. And by me saying transformations, what I really mean is this is kind of like, approximately like 3 raised to the x power. The problem is it's got a negative in front of it and a 2. And the x value is no longer an x value, it's x plus 4. And the outside is being subtracted by 1. So there are a lot of little transformations happening to the picture 3 to the x. Notice, by the way, I chose to write this not as p of t, but as f of x. That's a personal choice that I make when I'm creating a function, an exponential function that does not truly represent anything realistic. I would rather just transform to a function name that's very mathy rather than very realistic. And so I'm just using f of x here. Now to graph this function, you will go ahead and graph the base function, which is 3 raised to the x power. And when you do this, as I've always mentioned in the past with base graphs, plot 2 points. Very quick and easy to do that. It goes through 0, 1 and 1, 3. That's what 3 to the x looks like. Y equals 3 to the x. But those 2 points will be my anchor points. I will use those as reference points as I manage all my other transformations. So let's see. I have 3 to the x graphed. Now I'm going to go ahead and attach that in -2. That is, I'm going to multiply all the y values by a -2 to get my next graph in line. So the 0, 1 will become a 0, -2. And the 1, 3, again, you're multiplying all the y values by -2, will become a 1, 3 times -2, which is a -6. I'm just going to plot that way down here. 1, -6. Otherwise, it's just a reflected graph of that exponential. This is y equals a -2 times the quantity 3 to the x. And notice that the horizontal asymptote at y equals 0 is still at y equals 0. If you multiply y equals 0 by -2, it's still y equals 0. Another thing I want to mention here, very common rookie mistake made by mostly elementary algebra and intermediate algebra students, but not college algebra students. But if you want to make this mistake, I will tell you not to. These two numbers should not multiply. So I'm going to just write that in here. I see that from students that have very shaky mathematical backgrounds. The reality is that 3 is locked inside that as the base of that exponent. So it cannot be moved out from that x, nor can the -2 be moved into it because the -2 doesn't have an x power on it. -2 is being raised to the first, not the x. So you cannot glue those together. They are separate. Leave them as separate. Okay. All right. So now we are done with the highlighted -2 there. Let's go ahead and move on to the x plus 4. Now we're into the shifts, and we know that that x plus 4 moves everything to the left 4 units. So all the x values I'll subtract 4 from. All these x values, this x value right here and this x value right here, I will subtract 4 from them. And honestly, at this level of the game, I normally do all my shifts in one move, but I think it's kind of safe to go ahead and take our time here. So we had a point at 0, -2. We're going to subtract 4 again because we have a transformation on our function. We're going to subtract 4 from that 0 to be at a -4, -2. So let me go ahead and find my graph here. -4, 1, 2, 3, 4, -2, 1, 2. So there we go. There's our point. I was using blue. I'm going to label that -4, -2. The other point we had was 1, -6. And again, I'm going to lose 4 from the x value. So it'll be a -3, -6. well, we can see where negative 3 is along the x-axis. We're going to just drop, let's see, 1, 2, 3, 4, 5, and 6. So negative 3, whoops, wrong color again. That's negative 3, comma, negative 6. Again, because I only shifted left or right, specifically left in this case, it did not move the horizontal asymptote. So again, I still have the horizontal asymptote there. It is a function, so don't have it curl back on itself or anything like that. It has to pass both the vertical and horizontal line test, honestly, because it's a one-to-one function. So far that's what we have. And then our very last move is, oh, by the way, I should label that, right? So this is y equals a negative 2 times 3 raised to the x plus 4. The very last move is to subtract 1. So shift all the y values down 1 unit. And because this is my final move, I'll just make a bigger graph here. And notice where I'm placing my y-axis. It's because most of my graph is to the left of that y-axis, so I just go ahead and do that. Because I'm shifting everything down by 1, I'm going to go ahead and draw in here that my horizontal asymptote has been shifted down 1 unit. So this is y equals negative 1. It's critical that you note that for your instructor. Otherwise, the points are still negative 4, comma something, and negative 3, comma something. So I need to plot those out. Negative 1, negative 2, negative 3, negative 4. And the y value on that negative 4, comma negative 2 has been shifted down 1. So it's a negative 4, comma negative 3. Negative 1, negative 2, negative 3. So negative 4, negative 3 is right about here. Make sure you label that. And then the other point was at negative 3, comma negative 6. Again, it's just dropping 1 in a value, y value. So it's at negative 3, comma negative 7. So this is negative 3 right here, but I have to find out where negative 7 is on the y-axis. At negative 1, 2, 3, 4, 5, 6, and 7. So I'll try to line these up in blue. That looks pretty good. Don't forget to label that. It's a negative 3, comma negative 7. Otherwise, you pretty much have the graph. I do a lot of little etch-a-sketching here. It's going to be a very steep looking curve according to my drawing. And there you go. That is the graph of f of x, which is equal to a negative 2 times 3 raised to the x plus 4, then minus 1. There's not much else I can give you as far as graphing exponential functions. That's as good as it gets. I wish it was harder, but it just isn't. Again, I want to reiterate, you're not in the real world going to see exponential functions like this, because usually the outputs are populations, and populations don't dive into negative numbers. I'm sure you can create some special faux example where it does, but the reality is most of the time we do not deal with negative populations.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much. That isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.